recording.
Oh, it's doing it. Yeah, it's recording. That's done, I think.
So yeah, and if we all mute mics or whatever, then Tristan can say what's going on.
I'm not sure if... Can you hear me, guys? Yeah, I'm not sure if Tristan's froze. Bless him.
My whole screen's froze.
Yeah. I wonder if it's
Yeah.
Tristan's. He might come back in a minute.
Oh, bless him. They might be chatting away now, bless.
It's still recording, isn't it? Oh God, you can just see our faces frozen on the screen.
Hello. Are we back?
We're back.
Great. So I'll try that again. I'm not sure what happened there. And I'm going to try and share recording and transcription. Let everyone know they're being recorded. So you may want to not swear and don't say anything bad about anyone who you care about. And I'll see if I can share the screen. Can you see a PowerPoint?
Yeah.
Brilliant. Right. So, like I say, I hope it doesn't make things worse, and I'll just go through it. If there's anything that's not clear, just give us a shout, and I'm going to see if I can start it as a proper PowerPoint and hope we don't get logged off. Right. Are we still okay? Yeah.
Yeah.
So, I suppose when you're doing these statistics, you're trying to find something out. And because we're scientists, we tend to want to find out certain things. We might want to know if two groups are different from each other. And that might be, in our case, people who've had a treatment and the ones that had no treatment. And that might tell you if the treatment worked. Or it might be people who had this treatment or that treatment, and that might tell you which treatment's better. Because at the end of 6 months of this or 6 months of that, one of them's speaking fluently and one of them can't. And that you might say, oh, that's because of the treatment. Look, so you've looked at two groups. Or you might have if you're testing a drug or something else, it might be this group get the treatment and this group get a pretend treatment. They get a tablet, but there's no treatment in it. There's no medicine in it. And then that's really good, because then you get to really know, is it really the treatment or is it thinking you've got a treatment? And that makes you feel better because someone cares about you. And all of those things. So you're comparing two groups. And everything I think that we are doing is really about comparing groups. Is that all right? Great. I hope it is. Just let me know if anything's not all right. Great. Okay. Now that's when we're kind of doing an experiment. So we've got this group get this group get that. But sometimes we just want to know about the world, and they're naturally occurring groups that I didn't make up and put them in groups. They just are groups. Like reception kids are a group. I didn't put them in there. They just are there. And group 1 kids, well, they're a group and I didn't put them there. So they're naturally occurring, but it's still two groups. And I'm not doing an experiment really, because I didn't say you're going to get the treatment and you're not. It's not quite the same. But it's still the same kind of thing. I'm comparing two groups. And then there's people who've got aphasia, and then there's other people who haven't. And again, I didn't give them aphasia, so I didn't set up the situation. But I can still use them as groups that are in the world, and that might be useful to find out if an assessment works and what information it tells me. Okay. And there's other things, which is, I think, what we were getting to in the tutorial today, is it's the same group. The two groups are actually the same kids or the same patients, but just 6 months later or a year later. So is this group of people now better at word finding than they were 6 months ago when we started working with them? And then you can say, well, the treatment worked. Now you have got two groups, but they're the same people. So it's a slightly different situation. It's the same group now and then, if you see what I mean. And you, because they are so similar, they're the same people, you might have to treat them differently and use slightly different statistics because they're not quite different groups, and you might call that within groups, and that's what they refer to later. Is that all right so far? Yeah. So anyway, we're comparing two groups, and they might be groups I made, groups that just happen to exist in the world, or they might be the same group but at different times. But either way, it's kind of still two groups, if that makes sense. Right. Okay, whatever the question, it's always about a group. And we have to use groups because that gives us lots of data. And if we just look at one person, give them a treatment and they get better, well, that was because of the treatment. Well, not necessarily, because just someone getting better because you treated them isn't proof that it's good treatment. They just got better. And we all worry about that, especially with, stroke patients who get better anyway. And, so one thing happening once isn't proof of anything. So we have to look at groups. But the thing about groups is they're hard to describe because there's not just one result. So if it was just one person, you're comparing one person with another person, he got 10%, she got 50%, she did better. Fantastic. It's simple. There's nothing to talk about. There's no standard deviations or ranges or anything. It's just he got 10%, she got 50%. It's simple. But with groups, it's a bit different because groups don't all do exactly the same, even though they're all reception kids or they're all people with aphasia, they all do different. So to understand the differences between two groups, you have to use this horrible thing called statistics, which is what we're doing at the moment. Right, that's where the problem starts. You have to describe a group. If you want to compare two groups, you have to be able to describe this group, describe that group, and then say why they're different. And one number, 10% or 50% or whatever, that's not going to be enough because it's a group. Okay, so how do we describe a group? Well, there are first things, and the first thing we say is this thing called central tendency. Now, that's not a word I've ever used until this last week, but that's a group of statistics. And there are different ways to say this thing, which is the middle, or it's the average, or it's the main result. And those are the first one is the mean, the arithmetic mean, they call it. And you know how to do it on a calculator. You add it all up and divide by how many there are. So if you've got 10 results, you add up the results and divide by 10, and that tells you the mean. There's also this one called the median. And that's where that's where you line all the results up. There it is there. You line all the results up in order, 1, 3, 3, 6, 7, 8, 9. You find the middle one, and that's the median. And that can be useful as well. And there are different ways that's useful. It's not better or worse. It's just how it is. And then there's the mode. And the mode is the most common result. And you can see there, this is a group of results, 10 results, 0, 2, 1, 0, 0, 3, 2, and the most common result is 2. So those are 3 different ways of measuring the middle of the group, if you like, or the central tendency. For us, I think most of the time, we're kind of interested in the mean. But we might use the others to tell us information anyway. Is that all right with everyone so far? Is everyone all right with that? Oh, I saw a thumbs up. Fantastic. Is it just you now,
thank
Sarah?
you.
Is everyone all right?
Yes, thank you.
Yeah,
Right.
I get this too.
All good.
Great.
All good, Professor.
Good. So the idea is we've got these things, and so that's the measure of the middle. And that's fair enough. That's great. But there's more to it because hang on, how do you go to the next slide? Oh, so thought there was another slide there. Anyway, okay. So here's a made-up question. Here's a question: are basketball players taller than football players? Right, there's a question. Yeah, I mean, I think I know the answer. I've seen basketball players and I've seen football players, and it seems pretty obvious to me that the tall ones are the basketball players. But that's just my opinion, you know. So I need to check that. Is it really? Are they really? Okay. So there are two groups, and the groups are different. Okay. The differences are called variables. Okay. And there's the independent variable, which is kind of the one that I control, or at least it's the one that is known beforehand. Okay. And in this case, that's the sport they play. It's the independent variable. And that's basketball or football. Or it could be these other things, like it could be a treatment or no treatment, or this treatment or that treatment, or before the treatment and after the treatment. So it's the way I divide them up. It's the thing that's true about them. It's the thing I know beforehand, and it's independent. So they call it anyway. And then there's the thing that I measure, and I call it my results. Now, in this funny experiment here, that's how tall they are. And I call it the dependent variable. Now, it's not because how tall you are depends on the sport you do, although maybe it does, I don't know. But it's called a dependent variable because it's the thing that comes out. It's the results. It's what you write down. If you were doing a survey, it's what you'd probably call it your results, and you'd write it down, and that's your dependent variable. So in this case, it's the height of the players, but in our jobs, it might be how good they are at speaking or how well they do on a certain assessment. Or if you're a doctor, it might be, do they live longer? Can they walk better if you've done some surgery on them, or whatever it is? Okay. So there's two variables in this case, the independent that goes in, if you like, and the dependent that comes out, what you measure. Okay. To find that answer, I have to measure them. So there they are. There's my football players. And there's a whole range of them. And the more that I measure, the closer I am to the truth about football players. If I could measure every single football player, I'd know the truth. What does Jenny say? The true state of affairs or something about football players. If I could measure them all. So I measure the football players. There are some short ones. There are some tall ones. But most of them are in the middle. But I can't measure them all, obviously. To find the answer about player height, I measure them. But I can't measure them all. I take a sample. I take maybe 10 or 100. I take as many as I possibly can because that gets me closer to the truth. The more I look at, the more I know about the group that's called football players. Okay. Now that sampling thing, how I take a sample, I could do that. I think she did a whole session about it. I remember whole slides with pictures. It said female, 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 and female, and female, and female. And there was different ways of taking a sample. And there was random sampling, and there was stratified sampling, and there was maybe lots of other kinds of sampling. And that's really just, how do you choose which football players you're going to measure? I could just ask people in the street, are you a football player? Okay, I'll measure you then. But I only live in one place, and that's not going to be every football player. It's not representative. I could phone up people at random numbers and ask them if they play football. That's a bit weird. Or I could go to teams in the league and choose 2 members of each team at random, and that might be stratified. So I'm making sure I'm spreading it about a bit. I don't know, but there's different ways of sampling, and there are good and bad ways probably. But either way, even if I count loads, it's still just a sample. So it's not the truth about footballers, if you see what I mean. It's just 10 or 100 or a few footballers. Okay. So then I make a graph of their height. And that graph of their heights shows what we kind of just said. So there's a graph. You can see the height. I don't know if you can see my little cursor, but it's going along the height there. So there are some small ones, small football players, and I'm sure they're really good at dodging and ducking and weaving, and they're really good at that. And then there's a few really tall ones, and they're good at heading the ball and things like that. But most of them are in the middle there. And that's what this graph shows. It shows there's a few little ones, a few really tall ones, but most of them are actually around the mean. And that's why the graph is the shape it is. Okay, now that graph, you'd get the same shape graph with lots of different things. If I measured how fast they could run, there'd be some slow ones, there'd be some fast ones, but most of them would be about the same speed. And it's not just for football players, that'd be for foot size. If I measured everyone's feet, or how many words they know, or anything. There'd be people who don't know many words, people who know lots of words, but most people have got the same vocabulary and they use it. It's that shape. It doesn't matter what you measure. Well, not nearly everything, but lots of things show this thing called a normal distribution. And that's what it's called, the normal distribution. And it's called normal, and that's a bit like the word we use, you're very normal or something. But it's not that. It's not that it's usual or common, although it is. It's just called that. It's like a name, and it means something very specific. This shape, and that shape can be described by some mathematical equation. I don't really know what that is, but it's got a very particular shape, and it is common in nature. If you measure the size of pebbles on the beach, you'll get some tiny pebbles, some massive boulders. And most of them are about the same size on this particular beach. You know, it's like just a thing that happens because of the world. Now, sometimes, yeah.
Is there a way to, like, when you get your data or your table, if you don't have like your graph, is there a way to understand if the data is normal or not without the graph?
Yeah, and we come to that later on. And that's this thing called the Komoskikov-Smirnov test. And I mean, you could look at the data, a list of numbers, but you can't really tell until you plot it. And that was what I know in the SPSS, in these tutorials, we've gone to graphs and plot the graph. And some of them you can see they're all leaned over one way, and some of them they're all leaned over the other way. You think, oh, that doesn't look normal. It's just an eye test. You know, you can tell by looking at it. But that's not really a proper test, is it? Well, you know, you might have opinions, and that's not very good. But in SPSS, she showed us that there is a test for normality, and it had a funny name, which it was K and S, KS, and one of them was Smirnoff, I noticed. Okay. So there is a test for that, but and not all data is this way, because as someone pointed out, if this were male and female football players, it might be bimodal. There might be an average height for the men, a gap, then the average height for the women. Yeah, so you might get that shape. Or it might be some things you can measure and it's just random, so that the graph just goes straight across, you know, and that would be called uniform data. And she has got some stuff in the slides about that. So, but most things that we're interested in give a normal curve, you know. Yeah, and if it doesn't, it's because like with when we were doing about skewness, if the test was so easy that everyone got full marks, well, then you're not going to get a normal curve because everyone's, you know, at the top end. And if the test was too hard, like these MCQs, then everyone's down the other end, and it's like, well, that's not a normal curve either. But, you know, the test was too hard. No one could do it. Everyone got 0. So you see what I mean? But most things you measure in a normal way, natural things, they come out that shape for whatever complex reason. Okay. Right. Now, those basketball players, we measured them as well. And the graph's exactly the same shape. Look, it's exactly the same shape. But if you notice, I'll just go back. There, the mean is 177 centimeters. And now, the mean is 185 and a bit centimeters. So, okay, so it's still normal distribution. And there's still some short ones, even basketball players, there might be short ones. And there's still tall ones, of course, but most of them are in the middle for them. It's still the same shape, but the mean is different. The mean's a bit higher. So that's very interesting. You've got 2 groups, and they're football players and basketball players. They give exactly the same shape of graph, but the mean has gone up a bit. So is that it? Can we just take that? Is that the end of that? It just means that basketball players are taller. No shit, Sherlock, etc. Or if I did that, does that prove this medicine works? Oh, look, they lived a little bit longer. The mean of their lifespan is higher. If that's it. Or the ones that I treated with my special therapy, they all are better at speaking. Have we proved anything? That's what we're asking. Just because the mean's gone up a bit, does that mean we are sure that the test worked? Okay, so that's what we're asking. And the answer is no, we're not sure, because we didn't measure every footballer and we didn't measure every basketball player. We just took a sample, 10 players, 100 players, 1,000 players. It's still just a tiny sample. And if you take a sample, you don't know anything except your sample. So it's not enough just to look at the mean. We can't be completely certain about that true state of affairs. Just because the mean's higher for the basketball players, it's just a sample. Okay, that's the key idea. It was just a sample. And anyway, they overlap quite a lot. Let's have a look. The tallest football player is still taller than the average basketball player. And the shortest basketball player, well, you get the idea anyway. And if I'd chosen a different 10 football players, I'd have got a different mean. If I'd taken a different sample, I might have accidentally chosen lots of really tall football players and lots of really short basketball players, and it might have come out the other way around just by random sampling. So I've got a problem. I did a sample, I measured them, they look different, but I'm still not sure. So we need statistics to say if the difference is a real thing. And we use this word significant. Are they really different? Or is it just because of my sampling? Is everyone still on board with all this? Is that all right with everyone? I'm trying to take a sample. I've taken a sample, but it's not enough just to say the means are different. because group data also has a spread. Right, so distribution 1 and distribution 2, you can see them there. And what I've been saying is that there's a mean, and the big bold arrow in the middle there, that's pointing at the mean, and this is pointing at the mean. But in this case, the means, we can say they're the same, but they still look different. There's in distribution 1, it's quite a narrow curve. It's everyone's close to the middle. But in distribution 2, they're all spread out. There's some really short ones, some really tall ones, and the graph is much more kind of spread out. Now that is what we call a measure of spread, and you can see it in the results. They're still both normal curves. They're both normal distributions. If I kind of stretched it out using kind of just a visual thing, I could make them both the same shape. If I could squeeze this number 2 up or stretch number 1 out, I could make them the same shape, but that would just be artificial. They aren't both normal curves, but they've got different spreads. Okay, so then we have to look at that. Measures of spread. So we've already looked at measures of central tendency, and that was mean, median, and mode. 3 ways of measuring the middle. And now we're going to look at 3 ways of measuring that spread out, how spread out they are. Okay, and there are different ways of doing that as well, sadly. So there's the range, which is the difference between the smallest and the numbers, and then the largest, sorry, not the numbers, the smallest and the largest. So here's a set of results. You can see at the side: 7, 8, 65, 8, 4, and 7. And that's the range then goes from 4 to 65, which gives this massive range, 61, from all the way from 4 to 65. But when you look at those, you think, hang on, 65 is a massive outlier. So really, actually, most of the numbers are less than 10. So just by calling it the range and saying that's a measure of spread, it's a bit misleading, because it just depends on the very small number 4 and the really big number 65. And that makes it look like the numbers are all spread out over this massive thing. But well, it's not really, is it? It's just this one number, 65, that sticks out. So a range might be useful, or it might be less useful than you think, because it depends on outliers, ones that aren't really representative. I took another sample, the 65 wasn't there, and suddenly the range would go down to like 5 or something. So range, it's okay, and it might be useful, but it's not that useful. It only depends on 2 results. So there's a better measure. And this is what we go on about a lot, called standard deviation. And it's better because it uses all the results. It uses every result. It measures how far away it is from the mean, the middle, and then it does some clever maths, and then it spits out a number. That number is called the standard deviation, or SD, and it tells us about the spread of data. So that data there, distribution 1, has got a small standard deviation because all the numbers are close to the mean. Most of the players are the same height. Most people got the same score, or not very, there wasn't much difference. Everyone did okay on the test. They did in the middle, it's fine. Or distribution 2, well, that's a big standard deviation. There's lots of variation. There's lots of tallies, lots of smallies, and they're all spread out. Yeah, there's still most people are medium, but there's a lot more variation. And that could be, again, anything you're measuring. So standard deviation tells us about the spread. Okay, are we all right with standard deviation? Is that all right? Yeah, great. So that's, we use that a lot, but that's not the only measure of spread. There are others which we'll come across. Now this is getting pretty heavy, but if you can get your head around this graph, it's a really good thing to understand. So if you're okay, if everyone's been all right so far, I'll just talk about this just a little bit, if that's all right. If you if you've had enough of standard deviation, just tune out for a bit. But there's the normal curve in the middle. There's the normal curve. And you know the mean, we know how to calculate that, add them all up, divide by whatever. And we've just talked about this thing called standard deviation. So what does that mean? Well, if I've got the mean, and that, I mean, I think for those football players, that was 177 centimeters or whatever it was. That was the mean height. And say the standard deviation was 10 centimeters. Well, that means that from 177 plus 10 centimeters, that's 187, or minus 10 centimeters, the standard deviation, that's 167 centimeters. Between those two heights, 167 and 187, with 177, the mean in the middle, I've got most of the players. In fact, I've got almost 70% of the football players are in this small bit in the middle. And if I shaded that in, that would take a lot of penning to shade it in, because that's nearly, it's a big area. 34% and 34, well, it's almost 70%, 68.3%. Most of the players are within one standard deviation above or below the mean. That's, I mean, that if you can get that, yeah, you know, you're laughing. Is everyone all right with that? Or should I go over that again? Pretty brutal, this.
Tristan.
Yeah.
I was just going to double check. So I think when Jenny's been showing us, like, you know, some of the data in the tables, I think standard deviation is like a single number, isn't it, sometimes?
Yeah. Just
So,
one number.
Yeah, so if I'm just trying to get my head around that, if the number was like, I don't know, like 80.
Yeah.
what would that mean? Would that mean
So say, let's talk about these football players again, just because it's something I can visualize in my head. So say the mean was 177 centimeters, yeah? 177 centimeters. That's the average height of the football players that are measured. Now, standard deviation is given as one number, but quite often it says plus or minus, like above each other. It says plus or minus SD and then the number. And that means, so say the standard deviation was, we'll just go with 10 centimeters. That means that that 10 centimeters plus, that takes you up to here, which is 177 plus 10 is 187, or 10 or 177 minus the standard deviation, that's 167. Nearly all, well, 80%, no, 70% of the players are within one standard deviation of the mean. So it's a way of saying where most of the players are. Now, if in another group, the standard deviation was 20, well, then you've got a bigger standard deviation. And that means that this part of the curve, this middle bit of the curve is wider. That means that there's more variation. So the sample you got there with its big standard deviation shows that there's a lot of variation in those football players. Most of them are between 157 and 197 centimeters. There's a big range. So the bigger the standard deviation, the bigger the height range you need to have to collect 70% of the players. And it goes further than that. So let's have a look at the next one. I'll just move on. Sorry. There we go. So if I know the mean and I know the standard deviation, I can say things like 68.3, that's most of the footballers are between 165, I've put there, but it's between these numbers here. there, and there. Can you see my cursor? Can you see the cursor?
Yeah.
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 So there's the mean, 177. And I've put the numbers on now. So it looks like the most of the players are between that number there, which looks like about 165, and that number there, which maybe is about 187. And most of the players are within there. Look at the bottom axis. One standard deviation above the mean and one standard deviation below the mean. That takes in almost 70% of the players, all of those players there. And if I go to 2 standard deviations, that's all the way down to here and all the way up to there. That really is almost all of the players. 95% or more are within this height and this height. That's like, if you chose a football player at random, they're probably not going to be beyond, they're not going to be shorter than 155 or taller than 198. I mean, they might be, but it's quite rare. There's only 2% that are that short and only 2% that are that tall. So nearly all the players are within 2 standard deviations of the middle, the mean.
Tristan, even
Yeah.
though the numbers are much smaller, so like you said, 153, so the mean's 177, but 153. So would the standard deviation not be like whatever that is?
Yeah, so
16 or something?
I just kind of superimposed numbers on it to make the picture I wanted. So the standard deviation, let's see what it would be. From 177 down to 165, that's about 12 centimeters.
Yeah.
So that's plus or minus 12. So if I was
Right,
writing
yeah.
that, I could say that the mean is 177 plus or minus standard deviation of 12 centimeters. Then another 12 centimeters, that's 24 centimeters, takes it all the way down to here. And then another 12 centimeters would take it down to here. And then the chances of getting a player who's smaller than that, well, I don't know. It's quite rare, isn't it? Not many of them.
Brilliant.
So that's all I'm saying.
Thank you.
So we're just saying there are 2 bits of information, the mean and the standard deviation, that tell us quite a lot about the data. And then there's just more stuff there I could go on about. Now, there are other measures of spread, and she has mentioned other measures of spread like interquartile range. There's variance, there's one called standard error, but I don't think we'll need them. Not very much anyway. So I don't know much about them. So I think interquartile range is literally you line them all up, and it's the first 25 are the smallest quarter, the tallest 25% of the tallest quarter, and in between is the interquartile range. But anyway, we'll leave that for now. So the point is this: if you've got some numbers, the central tendency, which is the mean usually, but it could be the median or the mode, and you've got a measure of spread, standard deviation, or some other things, well, then we can describe the group. And then we can do statistical tests, and then we can say if it's really different. And then we can say things like, yes, basketball players are taller, or we can say things like, yes, this treatment does make people better than this treatment. Or, yes, I'm doing a good job because all my patients seem to get better, actually, so I'm good. And we can do those kind of things. But the mean isn't enough. If you've got a measure of spread as well, you can describe a group. And if you plug those into a clever test, it'll give you a result, and it'll tell you whether they really are different. So all those funny tests like t-test and Spearman, whatever, and Mann-Whitney U-test, and all of those, Wilcoxon and Hanover, All they are ways of telling if this group or that group are different. Are they really different? And that's what statistical tests do. But because there's different kinds of groups and different kinds of questions, and there's not all normal data, sometimes it's a bit skewed, and there's sometimes we have to use different tests. So there isn't just one test we can always use. That's what that thing is telling us. Right. Is everyone okay? Are you all right, Sam? I can see you there. Has that been all right for the first bit?
That's really helpful, Tristan. Thank you.
Right.
Perfect, thank you.
I'm just having a little look on like the decision trees.
That's coming up.
Okay.
That's coming up.
I was just gonna
yeah.
use that example because it's so much more helpful using a proper example that's just you can make sense of, like,
Yeah.
you know, instead of using quite a complex one.
That's coming up. So we'll do about how do you choose that. There's all these different tests.
Yeah.
They're all going to tell us, is this group different to that group? That's what they're all doing. But why are there so many tests then? Well, sadly, it's because the data, the question's different. So that's why we have to do those tests. And we'll come to how do you choose the tests in a bit. Is that right?
Yeah.
Right, okay. So before we look at the tests and how we choose them,